Hello everyone. Today we are going to talk about chapter 3, Introduction to SQL from the Database System Concepts 7th edition. In this topic we will learn about SQL query languages, SQL data definitions. These are more important in this course. You will be doing a lot of SQL operations throughout the course. So chapter 3 is really important for you to grasp. So a little bit of history. IBM SQL language developed as part of the System R project at IBM. They later renamed it the Standard Query Language or SQL. ANSI and ISO standard with SQL has SQL 86, 89, 92. The latest one we got was SQL 2003. So all commercial systems offer most, if not all, SQL 92 features plus varying features sets from later standards and special proprietary features. Not all examples may work on the particular system. Now let's look into SQL parts. So DML provides the ability to query information from the database and insert tuples into, delete tuples from, and modify tuples in the database. Integrity stands for the DDL, includes commands for specifying integrity constraints. It's basically saying data definition language. Each table, there are primary keys, there are foreign keys. Primary keys should be unique. No other key with the same values should not be inserted into the database. There are integrities that is managed by DDL. So that is integrity constraint. For then we have view definition. The DDL includes commands for defining views. Different users do different queries with SQL and gets different views from that same relation. So the view definition is defined as the DDL definition as well. Then you have transaction controls that includes commands for specifying and beginning and the ending of transactions. We have embedded SQL and dynamic SQL, defining how SQL statements can be embedded within general purpose programming languages. Then we have authorization, where this includes commands for specifying access rights to relations and views. These are part of SQL. So let's move on to data definition language or DDL. So what is DDL? The SQL data definition language allows the specification of information about relations, including the schema of each relation, the type of values associated with each attribute, and then integrity constraints. The set of indices to be maintained of each relation, security and authorization information for each relation, and the physical storage structure of each relation on the disk. So the schema of each relation basically saying, hey, this is my relation R, or this is my relation or table instructor, and this has attributes ID, name, department name, and salary. This is how the schema is defined in the relation. And then what type of value associated with each attribute. For example, ID, this should be integer. You cannot store characters into ID. Name should be at least of length 20. It should not be null. This kind of values associated like name, that is coming from data definition language. Now domain types of SQL. These are different domain types like character, variable character, integer, small integer, numeric, real, double, precision, float, and there are more that will be covered in chapter 4. So character n is a fixed length of character with user specified length n. So if it says character 5, that means it has to be of character length 5. Variable character n, for example, variable character n 20. Here the n is user specified maximum number length, but it is variable. So variable character 20 can hold values that are less than 20. For example, variable character 10 characters can be held into variable character 20, but it cannot hold more than 20. For example, anything that's characters length is greater than 20, like 25, 26, it cannot hold that. Then we go into numerics PD. Here we say numeric PD 35. 3 is the digit, and 3 is the p digits, and d is the digit of after the decimal points. For example, 31, or here say 31, so 4.5, that cannot be stored there. Similarly, 0.32, that cannot be stored there, because although we have three values there, but after the decimal there is 2, but we defined after decimal it should be only 1. So but only for 44.5 that can be hold, because 44.5 has 3 digits, but after decimal there is only 1. So that is a possible value that can be stored in numeric 31. Then real double precision, so floating points, float n. There are more of these domain types we will cover in chapter 4, and we will look how these domains work in our next slides. Now let's look into create table construct. Here SQL relation is defined using a create table command. Create table R with different attributes A1 and domain type D1 for attribute A2, domain type D2 to attribute type AN to domain type DN. And then we have integrity constraints. So R is the name of the relation. Each AI is an attribute name in the schema of relation R. D is the data type of values in this domain attribute AI. So creatable example for here we see instructor, here ID, name, department name and salary. These are the attributes that we want. And then character 5, variable character 20, variable character 20. This is how we say for each of these attributes what type of domain this attribute will hold. So instructor, create table, then the relation name, that is instructor, and then first bracket. Within there we have all the A1 D1s or A values and D values, that's the attributes, and then our domains, and we need to look into integrity constraints. These integrity constraints we will see in the next slide. Here we have ID character 5, so it has to be character 5 only. So that is the domain for this attribute ID. Salary says numeric 5, numeric 82, it only hold numeric value 82. So ID, name, department name, salary, these are the domains for this table. And character, variable character, voucher 20. This 20 means name should be at least of length 20. It can be less than 20. And here the relation name is instructor. So in definition we said integrity constraint, that is not shown in this example. So here we have only seen the attributes and the definitions or domain types of these attributes. So integrity constraints in create table: foreign primary key, foreign key, and not null. These are the integrity keys, integrity constraints. So foreign key references a table different R, and not null is basically saying this value cannot be null. So for example, name from an instructor table, it cannot be null. So it says not null over there. So these are the integrity constraints. These constraints are unique. Basically, they control how you update the table. You cannot break these constraints. These constraints define how your data should hold in your table. So we have primary key for each table. There can be primary key is unique, or there can be one attribute as a primary key, or there can be multiple attributes as a primary key as well. Here variable character voucher name is not null, and then we have the primary key ID. That means ID should be unique, and with the same ID multiple users cannot hold the same ID. And we also have a foreign key that says department name, and department name references to another table, that is department table. So let's look at few more relation. The student relation here and the takes relation here. So let's do one thing. Let's create tables in the simulation where we can uh, practice hands-on with these relations. And this is an open source website. You can go here and you can practice SQL queries. Here, if I run this operation, at the left side you can see the student table has been created. So this was not there before. So we have these attributes: ID, name, department name, and total credit. These are the attributes that this student table has, and these are the value types or domain type. This student table holds variable character 5, name is varchar 20, and it's not null. So name cannot be null, and total credit is numeric 30. That means it will hold 3 digits, but after decimal it will not hold any value because it says 0. And we have primary key ID. Primary key ID is basically saying, hey, this is for this table, ID is the primary key here. And then we have foreign key as well. The department name here is the foreign key, and this references to the department table. Look at if you look at left side, ID is icon as key, and rest of the attributes are normal. It's not key. So let's take a look what data do we have inside this student table. So let's okay, I made a mistake here. I didn't put, oh, I forgot to put from. Select star, that means select all. From where? From student table. So select asterisk means select everything. Now here we see there is no data, but we see the table definition: ID, name, for department name, and total credit is shown in that database schema. So select asterisk means select all. From where? From which table? From student table. So we see everything from student table, although we don't have any data in there right now. Now let's do one thing. Let's create the takes table as well. I copy that code from the slide into here. And then here takes has ID, course ID. And at the left, you don't see the takes table, but after we run this query, this table will go at the left and you will see the takes table is there. So these are the attributes: ID, course ID, section ID, semester, year, grade. We have total 6 attributes for this, and these are the attribute variable types, like what are each of the domains for this each attribute. So what we learned: create A1, create relation R with A1 attribute D1 value domain, A2 attribute D2 domain. This has a primary key, which is ID, course ID, section ID, semester, and year. Combining all this is the primary key. So this is a composite key. So these combining all of these 5 values gives me a unique key. We can have same ID, course ID, section ID, semester for 2 students, multiple students, but year should be different for each of them. Only then the constraint holds. The primary key should be unique. So all combining all 5 of these, we get a unique value. We can have different same ID, same section ID, same semester, same year, but course ID should be different. At least one of these values should be different to make it unique. Otherwise it will say, hey, with the same ID, same course ID, same section ID, same semester, same year, we already have a value in the database. You cannot insert this value again. We already have this data. So the primary key with this composite key says, hey, this is the primary key with all these values as your composite key, and they should be unique. And here, if you see, the student table has ID and foreign key ID references student. This says, hey, this ID from the text table, this is a foreign key, and this references to the student table, and student table has this same ID. And finally, we have another foreign key with course ID, section ID, semester, and year. This references to the section table. So this is also a composite key, but this is a foreign key. So all combining all these keys is basically a unique key. Now if you look at the text table, I created this with the composite key. At the left side, everything shows a key symbol here. Okay, we have one more table, like the course table. We can also create this course table as well. So the course table foreign key is department name, and this references to the department table. And we run this. The course has course ID, title, department name, credits as my attributes, and then okay, let's see how to update the table. You can insert data into table, insert into instructor values, and then you get the values. You can delete from the table like different tuples. You can also say delete by ID. You can drop table R, you can alter table. So alter table basically means you have already the table, you can modify the table with add more values. So let's try with something. Let's see, we just deleted the table course, so drop that course, drop table course, and we can write at the right side we have this code memorized. So what we ran before, we run it again, we add the course table again. So let's alter the table. So alter table R, add A, that is attribute, and D domain. So let's add one more value in the course table. So we don't have integer here in year here. Let's do this. Alter table and then table name, and then we have to, what do? We add. So alter table R, add, and then domain name, attribute name, and domain name. What attribute do we want to add? We want to add year. We also want to add the year, but what kind of domain? Oh, I made a mistake here. Maybe we don't need the curly braces or the brackets here. So we just say attribute, add this attribute year, and type is int. We remove this from here. We also remove this. Run this. Now if you see, course has that year mentioned. Now if we add the year, for example, if we have 50 tuples in this table, and then later on we added year, what will happen to all those 50 tuples where year was not there? We will have null values over there. So if we added attribute later on, the values in the table becomes null. But we can update that with the queries as well. Now let's remove it. So we can just, oh, it didn't remove. Oh, for removal we don't need to give the variable type, because we already defined the attribute. We don't have to say what kind of domain type it is. So we remove the domain type and we can remove. See, now it removed, and we don't have that value in the course table anymore. Now let's see, select everything. Select asterisk means select everything from student table, and we don't have anything in the student table. Let's do one thing. Let's insert some data into the student table. I have prepared a query where we have 20 student data. So how do we insert it? Insert into the table name and then values, and then we add the values. So I have this query where we have, hey, insert into student table, and what are the values, the sequence of the values like ID, name, all that, and we have 20 values as 20 different tuples that we want to enter that I have written here. So these are all random data that I generated. If I run this, now the student table has all the data that we need and we can run queries on it. Now select all, select asterisk means select all. From where? From student table. If I run this, now we see all the data of the students. So basic query structure is select attributes from which relation and where P is the condition. A represents an attribute here from R basically represents the relation like table names, and P we call it predicate, but we also call it condition based on what condition do we select. So we have seen this in the code example. Select asterisk means select all, and then we can also say, hey, I don't want to select all, I want to select specific attributes, like attribute a1 a2. So we can do that. So instead of doing all, we can say, hey, select. We want to select the name, for example, and then we select department name as well. I don't want to see the ID or total credit, I just want to see name and department name. We run the query, it shows me. It's similar to what we learned in the projection of the relational schema. Now we say, hey, I want to select these attributes from this table where department name is computer science. So I want to see only the students who are from computer science. We can run that as well. So this gives me only 4 data based on who are in computer science department. I want to see total credits, how many credits they took in computer science department. I can do that. So this gives us select attributes from which table and based on what condition. The select clause lets the attribute desired in the result of the query corresponds to the projection operation. We solve the relational algebra. Also, the SQL names are case sensitive. So, for example, if you say name with different capital letters, small letters, it will give us the same result. Let's try that. Select name from, see, we can select the name only, but now we will try different capital letters, small letters for the name. If I run this, still the same result. If I change again and run name again, still the same result. So now let's try one more thing. Select department name. So department name from student, it gives me all the department name. See, we have the repeating department names. For example, computer science is here again, and now here again. So this is not giving us distinct names. So there is one thing in the select clause, a distinct keyword. If we use this, it will give me the department name that is only unique. Let's try this and run this. Now we got the department names that are unique. This also has a keyword called all. This also gives me, but this gives me all the department names, not unique. And then we can remove that. It also gives me the same result. We have already seen this. Select asterisk. An asterisk is a select clause denotes all attributes. So instead of department name, we say select asterisk. That means select everything that is inside the course table. We got all the data, all the columns. An attribute can be literal with no from clause. So we say, hey, select. I say a unique ID, for example, S001 without the from clause. This gives me this ID, and this attribute name is also same. But I would say let's change the name to something else, as random. Now if I run this shows me random as the name. Now if we include the from clause for this literal, this will give me the same thing, but for all the we practice the slides example as well. Select 437 as foo, but now let's try with all the from clause from students. If we select from students, there are 20 tuples in my students. This will give me 20 of the same thing, same literal. See, same literal 20 times. Now I want to see the student name as well, and then run again. Now I got the student name, and this literal doesn't change. See, we don't have this value stored in our database, but we can see this as a literal. Now what we can do is in the select clause we can contain arithmetic expression involving operation plus, minus, multiplication and division, addition, subtraction. An operation can on constants or attributes of the tuples as well. So for our example, if we want to say, hey, select everything from student, we got total credit. In the total credit, I want to see how much tuition fees they paid for each student. We don't have the tuition fees calculated inside our database, but we can calculate that and create a view out of that. So let's say select, I want to see the ID, name, and then how much they paid. That is total credit or dot cred, this column over here, times, for example, each credit is $300 per se. So we calculate that by multiplying 300. And if we run this, we will get the tuition fees. This says total credit times 300. We want to rename this as tuition. So as tuition, if I run again, this says, hey, this ID, this student, this is the tuition fees they paid. Remember, this tuition value is not stored in our database, but we have total credit. We calculated that with the arithmetic operation in our select clause. Now with the select clause, we can also add where clause. That is basically the condition. I want to see based on different conditions the data. We can use where clause. The where clause specifies conditions that the result must satisfy. We have all this data. Now we add the where clause here. Select from where based on some conditions. Say I want to see the tuition fees who are paying more than $10,000. If I run this gives me all the students who are paying more than $10,000. Now I want to say, hey, I want to see who are paying less than $10,000. That's just two students who are paying $9,000. That's basically less than $10,000. Now I want to say, hey, who are paying more than $10,000 and condition. We can combine multiple conditions, and who are from department name is computer science, like who are from computer science and paying more than $10,000 as a tuition fees. If we run this query, this gave me also two results, but I want to make sure that they are from computer science. I can write department name in the select clause, and that will show us like which department are these students from. If I run this, now I can see. Now I want to see tuition fees for all department. I can remove this and clause, but I want to see who are paying more than $10,000. Yes, so I see all the departments name as well. Here they did with computer science and salary is greater than 70,000 for instructors. This is a different example. The from clause. Remember in chapter 2 we learned about Cartesian products. So the from clause, select everything from the from clause, but without defining condition, where basically we can do the Cartesian product. So instructor and teachers, we combine everything with the instructor and teachers. We got lots of data, but a lot of data did not make sense because there were instructors who were not teaching those courses. With the Cartesian product, we can do same thing in the SQL queries here with creating Cartesian product where each of these columns and rows. So I have this query prepared. In the takes, I have around 30 data for each student. They're taking what courses. For each student I created like multiple entry points. Now if we inserted the data, if we write select everything from students comma takes this, and without the where clause, it's basically making a Cartesian product. So all the students and all the takes, they will combine both of them. This will give me lots of data. There are 20 students, 30 takes. There should be around more than 100 or around 120 tuples here. So if you look at the IDs, a lot of ID doesn't make matches. That means it doesn't make sense because the ID was the foreign key here, remember when we created. So this student, the first two columns, this matches this ID, and this ID, this matches. That means this student is taking this course. The second one is also same ID, it matches. That means this student is taking this course. But the third one, you see the ID does not match. That means this student is not taking this course, and this tuple doesn't make sense. So this is the problem with the Cartesian product. Now we can do with the where clause, where we can define and then we can say it will make more sense. Where, I forgot to write where, and then student.id equals to takes.id. Now if I run this will match with this ID and give me all the join operation. Oh, I forgot to put a semicolon over there. Oh, I forgot to remove the semicolon over there. Yes, now run. Now this table makes more sense. So we don't have 120, but we have the values that makes more sense, that are valid. So this ID is corresponding with that ID, and these students are taking these courses. So this is equivalent to the join operation in relational algebra that we learned in chapter 5. Oh, sorry, chapter 2. We can also add more condition in the where clause. For example, if we say, hey, I want to see uh, what computer science students are taking, which courses are they taking, so I can add that as well, where ID matches this and department is computer science. Now if I run, I get all the students from computer science and take what courses are they taking. So this was it till today's class. In the next class, we will learn more about SQL queries with starting from the rename operation. Um, if you have any confusion or you want to reach out, just email me. We can arrange Zoom meeting and clear any confusion that you have. See you in the next class.